Hello, my name is Steve Boyd. I'll just share the screen a bit with you. I'm going to give a presentation on how to use 3D image registration for a longitudinal database or longitudinal studies using high-resolution PQCT. So let's get back to the slides. What I want to give is a bit of an overview. In fact, I'm going to see if I can make this work with the purpose of this presentation is to give an idea of the workflow for doing 3D image registration, how to extract the morphological results after you've completed the registration, and then making those scripts that I'm talking about available for users to download or contact me to get a copy. This is not a beginner's course, so people should be relatively familiar with how to use IPL on the Scanco systems. This webinar is totally focused on Extreme CT2 image data. Mostly it works for Extreme CT1 as well, as I've shown here. There are some subtle differences though, particularly with the morphological analysis that make it a bit different. So you should already know a bit about IPL to be able to take advantage of this, and you should also know a little bit about Python because you're going to have to do a little bit of processing off of the Scanco system on your own computer. I'll show you how you go through those steps. But before we get there, I want to just give a bit of a background of why we want to do the 3D image registration. The challenge when we use such a small region of interest from our Scanco scanners is that capturing the same region of the bone at multiple time points in a longitudinal study is, although pretty good, never perfect. And the positioning of the person in the scanner at each time point can be supported or helped using the scope view, but 3D registration really is required if you want to get a perfect alignment between scans. So you're always measuring exactly the same region, and this will maximize the reproducibility in your studies. A long time ago, I had some fun doing a study where we just looked at the variation in the morphological parameters using cadaver data if we scan slightly proximal or slightly distally. And for both the tibia and the radius, it makes quite a big difference in your results. And so that's particularly important in the radius. So it sort of emphasizes why you need 3D registration. Otherwise, what you end up doing is when you scan somebody, for example, 4 times, is you're not comparing the exact same regions. And so there's some noise in your data. And if you do the 3D registration, then the apples don't quite line up, but ideally you're comparing apples to apples. So you get a really good measure of reproducibility. The downside, I guess, though, is you do lose a bit of the scan region, but ultimately you should be able to keep at least 90% of the scan region and still get very good results. So there already is a built-in system in Scanco for doing some alignment, and it's called slice matching. Basically what it does is if you have 2 scans, it looks at the cross-sectional area of each slice in the scan, and then tries to match the 2 scans so that the cross-sectional areas are optimally overlapping. And so this kind of approach, you can imagine, works well for longitudinal misalignment, but if there's any actually rotation of the bone, which is quite often, that would happen slightly. I mean, we're talking angles of maybe 1 to 3 degrees, but they make a difference. And that's not captured with the slice matching approach. So the overall process is described here, and I'm going to whip through it a bit right now and then go back looking at the scripts. But if you have longitudinal data sets, and I'm going to use an example where we can have up to n data sets, I'm going to go through a specific example where we have 5 follow-up scans, 5 scans in the series. What you do is 3D image registration, and you align the baseline to the follow-up scan. And the different colors there represent the overlap between the 2 scans. What we need to do, though, is within each of those scans, the baseline and the follow-up one, is we need to define the entire volume of the scan and how those overlap, not just the nice, pretty image I showed you there. And that sort of semi-transparent box, I can use the screen here, is actually the common region between the baseline and follow-up. Now, it's really important when we do a morphological analysis eventually, we always do the morphological analysis of the original scan data. We never transform the scan data. We always transform the masks that identify which part of the image that we want to do the analysis. So there's a big difference there. It's an important one. So This works well. We have two, baseline and follow-up. We can identify the region, but of course we have more than one. And so we have another scan. We typically register the follow-up, the second follow-up, also to the baseline. And then we do the same process. We define the common regions. This box here is slightly different than this box now, because this is the intersection of this follow-up 2 and baseline, and this is the intersection of follow-up 1 and baseline. And then we do the same thing with all the scans. And we eventually generate all of these unique boxes that are occurring. Then what we do is we find the intersection of all these boxes. We can define this box in the baseline image space. We find the intersection of the boxes, and we define the common region there. This now is our golden region of analysis that we have to transform forward into each of the time points. And when we transform that, or in the case of the baseline, there's no transform required now, excuse me, we can then identify the volume of that baseline scan that is common amongst all the time points. And then we take this image here, and based on the transform between baseline and follow-up, we can transform this mask forward. And this mask is the identical mask to this one, but slightly transformed, identifying in this scan time point what is common. And you do it for all the follow-ups. So after doing all of this process, you are able to identify the exact same regions of interest within the bone. So that's a bit of a complicated process, especially when you want to optimize it for different numbers of scans. Even a baseline and a follow-up, you have to be very careful about how you define common regions. People are tempted sometimes to just shave off the green part here, and then maybe the equivalent shave off the red part in the baseline scan. It won't really work. You need to define these common regions. So this is just a little bit of showing its application in some in vivo data. So I'm going to use a lot of vitamin D data from a study we did recently to illustrate the effects of the registration. So we have, in this case, 5 time points, 0, 6 months, 12 months, 24 months, and 36 months, and the BMD as a function of those time points based on the scans. If we just scan the person and don't do any registration, then what's going to happen is we get a little bit of variation here. And this is very unlikely to be a physiological change in the bone. If we use the slice matching approach, so the green now showing slice matching, we get a bit better, or something that maybe looks more of an approximate of something that could be physiologically happening. This is a bit of a dip here, but maybe it's constant and now we're losing bone. If we use a 3D registration, it becomes more clear in red. You have more of stability here, and then it slowly decreases in bone. Excuse me, I don't know where this cough has come from. Now, here we show another example. And in this case, actually, it's cadaver data. And what we did is we just wiggled the bone at each time point, quote unquote time point, and did our measurements, first showing it without registration. Then we showed it with slice matching. We see a little bit of a trend, a change in bone happening here in terms of BMD. But when you do 3D image registration in a cadaver bone, what you should get is no change. And that's what this nicely shows. You need to use the 3D image registration if there are any angular misalignments. If it's purely axial, slice matching does a good job. But even a couple of degrees, and we've shown in other stuff, in a project actually that we're working on right now, that even 1 to 3 degrees makes a difference, okay? So you do all of that registration and you think you're done, but you're not, unfortunately. When you do a standard morphological analysis with ScanCo, the morphological analysis is, after slice matching, goes through what we like to term a black box. And from that, we calculate all the parameters. In this black box, a lot of processing happens that, you know, if you give it the Gobi mask and you give it the original AIM data and as well as segmented AIM data, then it can use combinations and permutations of that to calculate things like thickness, separation, etc. We can't use that now because the common region for each of these scans is no longer a perfect stack of 168 slices. It's actually shaved off in various angles, as I showed in the previous slide. So we have to replace this black box with something that is implicit for the registered data. And so after 3D registration, we have written, whoops, what just happened there? We have written custom scripts that will perform the morphological analysis. We capture the morphological analysis results in log files. In a typical study, so for example, the vitamin D had almost 400 people in it. measured 5 times, that's 2,000 time points. At 2 sites, that's 4,000 time points. Each one of those had to be, in series of 5, had to be registered, logs created, and then we have to extract the data from the logs to get all of our results, BMD, trabecular number, and trabecular thickness, etc. So even that part's not quite trivial. So I'm going to show you how to do that, though. So a couple of papers I just wanted to talk about here briefly. One is, this is an original paper from 2006 where I started working on 3D registration issues in micro CT data with animal work that we were doing, rats. Then very recently, Tanis Kemp published this paper where we never got around to actually illustrating how well it works compared to other approaches, compared to slice matching. And that's what Tanis did here in this study. It's just been published, so it's still in print. It should be out anytime, I hope. And then we implemented the 3D registration approach. Probably the biggest impact it had was with our high dose vitamin D paper, where we looked at 5 time points in a group of, well, in this case, it was 311. We didn't use all of the subjects in the study to look at bone changes. And I truly believe that without the 3D registration, we wouldn't have been able to detect had the sensitivity that we did there. So it can be very useful. So how do you do it? Well, part of the problem is, and part of my reluctance sometimes to pass on how to do this, is we're not set up with our directory structure in Calgary like many people are at standard Scanco sites. So we, like everybody else, have a measurement directory. In our case, it's called DISC2. Our username is called ExtremeCT2. And in that we have measurements. So these are sample numbers. And for that sample, in other words, a participant, we maybe have done 2 scans. In this case, I just said maybe it was a radius left and a tibia left. And then for another person, a different sample number. Oh, actually, I should have changed the numbers there, but it's the same sample number. But a different sample number, we might have done 4 scans or something for them. So this is the directory structure that's used for the measurements. So of course we do that as well, but then we have a separate disk where we transfer all of the, whoops, where did that go? We transfer all of the images that are in these directories, all the Gobi files, the Sega files, the AIM files, etc. We transfer them all into what we call a project disk. And the project disk is where we just assemble all of the data in one place in kind of more logical directories so we can work with them. And we also rename our files so they're more meaningful than file number 12293. We might call it vitd_0148, patient 148. So I'm going to show you that file structure here. So this looks a little onerous, but in our project directory, in our case it's disk 4, under the username Bone Lab, for all the people who are working in the Bone Lab, we have a project that we call vitd in this case as an example. And in that project directory, we would typically have 4 subdirectories: a com, models, log, and doc directory. And I'm going to go through each of those separately. The com directory is where we store all the scripts that are specific to this study. The model directory, which I'm showing now, just ignore everything else, is where we store all the image data in this directory here. When we're doing registration, because not every study needs registration, we'll create a separate subdirectory called register. And in that directory, we have to structure it so we have all of these subdirectories. These ones here mean month 6 registered to month 0, month 12 to month 0, month 24 to month 0, month 36 to month 0. These I'm going to explain shortly what these files are. So that's a models directory. Then we create a log directory. And in that we have various subdirectories where we've called our morphological analysis just internally. We never planned on sharing this widely, but we call it our Calgary Analysis. So that's a subdirectory we call it there. And then I have various log files that get stored, and it's just a way to go back and check that things went properly or so on. I could go into that in a bit. Then we have the doc directory. Doc directory is where we keep images. We'll have 2D or 3D images. In this case here, we had some images showing AIM files and ISQ files. Just a quick way, like I just said, we have almost 4,000 images, so 4,000 scans. So we have to have a quick way of viewing them all. So we automatically generate 2D images, or we automatically generate 3D images. we might want to check, does the goby that segments the cortical from the trabecular region seem reasonable? A lot of that is automated using our auto contouring. And, you know, most times it works well, but you have to check every one to make sure it worked properly. Was the segmentation correct? So we do things like that. So then to be able to do the 3D registration, we have a lot of scripts, and that's what these are all named here. Some of the scripts are for the processing, and I'm going to show the workflow for the processing in a second. And so that's what all these are. Some of the scripts are for generating prints. That actually extends to here, these scripts. So 2D and 3D images that I was just talking about. And then we also have some scripts. These are non-IPL scripts. These are for running on my PC, or we use Mac laptops usually, but it doesn't matter. It's Python. And we run these scripts to grab the important data out of the log files. And I'll show you a bit about that in a second. Typically, all these files, except for these ones here, would be in our COM directory for that project. And quite often, if we have another project that we call T-Bone, where we measure longitudinal changes in astronauts, we use the exact same techniques, and we'll have a separate project disk, and we'll start out by copying these files to T-Bone, and then we'll slightly modify them to our specific data sets that are specific to T-Bone instead of VitD. You'll notice that in these files, we have a structure that's always the same. We call this file here, called IPL register xt2, is what's called by our submit all register script. And so in this script here, submit all register, we will call this script 4,000 times, or however many times we have to do it for the study. Same thing, submit all register concat. That's talking about concatenating multiple of those sort of wonky cubes. We'll call this many times, and so on. So the submit all is what we submit to the queues so we can process things. And these are the base, let's call them scripts or little programs that are doing the job thousands of times for the project. And there's somewhat of a parallel here too. Some of these IPL scripts can be used for looking at either AIMS or ISQs. So it's still submit all print 2D, and both of them will use this script here. So it's close. And then these are completely separate. So that's the end of those slides. What I want to do then is talk a bit about those scripts. So what I have here is a file that is going to be available to people too, that shows the process. The flow, and this gives a bit of background, but it's very limited. The flow is, first we have to do the registration. If we go back to, actually I'm going to go back to this slide here, slide 7, I think it was. Yeah, for this slide. First we have to do the registration, then we have to concatenate everything. Then we have to define new gobies based on the concatenation, and that's done by taking this cube that's specific to follow-up 1 and the original gobies that somebody generated when they were doing the original analysis, and just slightly shaving off those gobies so we only analyze the region that is common at follow-up 1. And we do the same thing for follow-up 2 and follow-up 3. And then we actually run the morphological analysis with those gobies. I'm not showing gobies here, but with those gobies so we can get data. So we do the registration, we concatenate, we get the gobies, we do the morphological analysis. Finally, actually what we also do is sometimes it's useful to know how much overlap there was in a time series. And so that's quite simple. Once we have a common region that we can look at each time point, we can find what % is that common region of the baseline maximum region, 168 slices with no registration. So this is the directory structure I showed in those slides, and the models structure that I showed in those slides, log and the COM. So all these files, I think I might be missing some files in this list, but that gives the idea of what's in the COM. I say here, it's really important to generate 3D images as you're going through this process, because if you don't, it's so easy for a mistake to happen, or 95%, or I'd say 98% of the times registration works fine, but if 2% of the time it's not working fine, if it misregisters, you've got to catch those, otherwise it will mess up with your data. So in the first step, we do the registration, and in the registration we'll have a file. Let me just show you some files here. If we have the IPL register xt2 and I open it up, then a little bit of history here of where it came from. Bert van Riebergen, this is the actual, just the registration, aligning the two. It uses IPL, And to be honest, in this whole script, you can see how long the script is based on this here. If we go down into the script, down here, here's the image registration. This is the part that does registration. That's all. And it's fantastic that it's implemented in IPL, so you can use that. Everything else is doing all of the steps needed to actually use this registration data, which is complex. And so you can read through that file if you want to understand what it's working, how it's working. Otherwise, you may just want to, understand the basics of it. Every script, I try to have a little bit of an information about how to use the file. If you run this on the IPL system, on Scanco system, without any arguments, you run the script without any arguments, it'll just regurgitate all this information, so you can just read it straight into the text. And it's basically saying, one of the things you might want to do when you register is sometimes you might want to register two parts of the bone rather than the whole bone. So what I mean by that is maybe you only want to use the trabecular region to align a baseline and a follow-up, and not to use the whole bone. And that could be, for example, case in pediatrics where you're a little concerned that if you register the whole bone, you might sort of negate any growth that's happening through the registration. So by using these gobies, you can actually define or focus where the registration will actually occur. So this is the registration script. It does a lot of things, including somewhere in here, I'd have to go find it. It prints out the actual image of the registration. And then the submit all, where's the submit all register here? What this does is it defines some parameters here. For example, it defines where I want my log files to go. And it defines where my analysis directory is, where my model directory is, where the raw data is, in other words. What the script that I want to run, which I keep in the com directory. And then I have, some go-to statements here. I've actually edited down these files a lot because they're, thousands and thousands of lines. I just showed sort of the fundamentals of how it works. But these are basically from month 36 to month 0. And I noticed actually I accidentally deleted the month 12 to month 0 here, but somebody else will recognize that hopefully. I define the analysis directory. I define file 1 to file 2. So I'm registering month 36 to month 0. These are parameters that go into this line here. This line here basically uses all those variables that were defined at the top to basically submit the script to the queue and run it. And so quite often, once we've got everything sorted out, and incidentally, when I say everything sorted out, things will often go wrong. What we can do is we'll do a little bit of a test. So I might run this script here just to make sure I've got things figured out so I don't run it incorrectly. And then once I'm happy with the test, this is truncated, but this used to be about 4,000 lines. So I don't want to submit that to the queue until I'm sure that it's going to work. I just here, what I did is I just showed for my own reference, when I had time series of data, I just, this used to be a lot longer because it's only showing, 3 subjects or 4 subjects from the study. But sometimes, a study subject didn't come back, or we lost a data set, or something happened, or I discover there's too much motion artifact and I want to exclude it. I use this as a table just to remind myself what was excluded. If I changed the letter to VT-VIT-M, so I knew it was a motion artifact challenge, so I would exclude that out of the registration. I wouldn't even do the registration with it. If you find, for example, overlap, you've got, typically you should be getting over 90% overlap easily. But if you have poor overlap, it might just be because one of the measurements in the time series was misaligned. If you exclude that one measurement, then you can, in this case where we have 5 time points, we can still do a longitudinal analysis on the remaining 4 and get excellent results. So if you can discover which is the image that's not working, then you can exclude it. So I said I often check. Here's where these are the kinds of images we might see. And these are ugly, but they allow me to quickly do this on my computer. I would literally have hundreds, if not thousands, of these things, and I would just look for anything that doesn't look properly aligned to me. So this is actually a pretty good registration. Nothing wrong here. And when I see misaligned, I mean one is 90 degrees to the other. Sometimes strange errors happen like that. But I'll create all those images and check every single one in the series. It's really important. I'll also check gobies after. And again, ugly colors, but the point is just to be able to literally do what I'm doing right now, flick through really quickly and look for obvious errors, you know? So by doing these kinds of creating all these images, it's a really good way for large data sets to make sure everything's okay. Was the segmentation okay? Did we accidentally missegment things? So I'm going through different time points and 2 views for each time point, and I see the different kinds of bones here to get an idea of the segmentation. So that's what is shown in the doc directory. By the way, the 2D stuff is not so important, but I use that. I didn't choose a very good range of colors, so that's why it looks so faded. But it kind of shows some 2D images, and you know, you can use that. For example, looks like there's some motion artifact in this image. You could look at those. So in the logs, after we do a registration, I could open up each registered log, and I can, if you want, you can read through this entire log file. And this will be really helpful for debugging a problem. It'll show errors and things like that. So the logs are helpful. In some cases, the logs, for example, overlap is actually used to quantify the amount of overlap. So in this log somewhere, we probably have measured volume, which it looks like it's right here. So the volume. And so we might need to know the total object volume. And we might want to find out what that volume is at each time point, and then we can know how much overlap we had. So the register is just useful. The other very important one, though, is the Calgary Analysis. And these files are actually containing data that I need to extract. I'll get back to that, okay? So let's close that. The next stage, I'm going to go back to this file here. After I do the registration, it will, after I submit the registration and so on, the results will get stored in a subdirectory. For example, if I'm doing registrations between month 6 and month 0, or month 12 and month 0, okay? As I said, check each of those images, make sure it's working. Now, if the registration didn't work, that can be a bit of a challenge sometimes. You can play around with the registration script. You can actually, you know, that little section of the actual registration that I showed you in the original, in this script here, IPL register XD2. You know, the actual registration is just this small part here. You can actually run that manually on your command line and try some different options to see if you can solve it. That's usually the easiest way. If worse comes to worse, what we do actually is we try to give it a better initial guess, and we have a tool that we developed at the lab. You could actually download it from the GitHub repository. You know, I hope you know what you're doing, but with this, we can bring up the 2 images and we can manually rotate one image into the other image's space and estimate what that transform is, and use that transform as the initial rotation, initial translation, so that it starts off closer to the actual result. I found with the entire vitamin D study, we probably had about 3 pairs of images that were challenging to register. The thing that happens sometimes, though, and it can happen, is a mislabeled image. A radius might be labeled a tibia, and obviously they're not going to register well together. So it really is good for catching any of those blunders that can happen sometimes. So anyways, this is the tool we use. So once you have the registration, then you run the concatenation part of it, okay? And that's where you're concatenating those funny boxes. And the output of that will be some files like this. These are basically, those files are basically these boxes here, these white boxes. Oops, how do we get back there? So, and those files are what are used in conjunction with the original gobies that you've created and carefully checked for every scan, to create a new set of gobies, the original goby, trab, or the whole goby, trab, and court gobies. And we store all those in the register directory, core goby. In the models directory are actually the exact same file names as these ones. So you have to be a little bit careful. You never want to overwrite these ones if they are in the models directory. You want to create new ones that are here. And that becomes very useful to have both the originals and the new ones, because then what you can do is when you do the morphological analysis, you can say, no, I'm going to use unregistered data and quickly run it. Or you can point it to these gobies and say, I want to use these gobies and quickly run it. Okay? So what else do we have to do here? Once you've done this, now you're ready to run a morphological analysis. And as I said, if you're using sort of the black box approach, you would hit submit. I can't remember what the exact script is on the UCT evaluation, and it would do the full morphological analysis, cortical and trabecular separate. This is where the difference between XT1 and XT2 becomes a bit more complicated. The way we do the analyses are different. But with XT2, it can be sorted out for XT1 as well. We've done that, for example, with our chemo study. So what we call it, just because it's to distinguish it from the Scanco analysis, we just call it our Calgary analysis. That file, let me see if I can open that. IPL Calgary analysis. By the way, I've got two here. This file here calls the gobies that were in the register directory. This file here is identical to this one, except it just redirects. In fact, we can open that one. It redirects somewhere in here to the directories. I'm not going to find it quickly, but basically, oh, here it is. It's redirecting to the gobies that are in the original models. Actually, this isn't it, but it's in there somewhere. Okay, it must be down here. Yeah, the red register gobi. So we want, in this case, we define where we're getting the gobies. I have to double check this, but that's basically the only difference is the line here. And for some reason, this doesn't look right. This is the register one. Yeah, this looks right for the register one. I think I might, well, we'll have to figure that out. Oh, that's what it is. It's defined. We just define it here, which directories we're going to use. Okay. So we use the regdir parameter instead of the dir parameter. We've defined the regdir parameter, and here we've got the regdir parameter, but we nowhere do we actually use it in here, even though we've defined it. Okay, so the difference is just on these three lines here. So once we're into this file, what it's doing is a morphological analysis, and it calculates all sorts of things that you would normally expect. You know, BMD. It would do actually here. It might even do the segmentation for you. And the auto contouring. I can't remember if we run that all the time, but I could just look at the script to figure it out. I'll let you do that if you want. But then after we've got the segmentation done, we come down here, and now again more preparation for the analyses, and then we finally get, where is it? The evaluation. So now we're going to start actually measuring things. And this will go into the log file so that I can find it in the log file, but this is where we calculate trabecular thickness, separation, and number. And it's just calling the actual IPL scripts to do it. Number, and then we calculate cortical thickness and cortical porosity in here. I guess I have it repeated. This is just for me to read in the script, and this is what gets dumped out onto the log file, and so on. And then we calculate all the BMDs and stuff like that, okay? And so finally, we get some of the areas. Now, there is a bit of a challenge, cortical area, trabecular area. There is a bit of a challenge when you're dealing with the extreme CT with the registration data, is because you've shaved off edges that were not part of the common region. Calculating the cortical area on each slice is not trivial anymore, because some of the slices only are slightly cut out. And so what we can do is actually, we could define exactly where we want to measure the cortical areas, trabecular area, etc. For now, quite honestly, we don't find the area being a very useful number, but it would be easy enough to just say, use the middle 50% of the images to calculate those areas. Somebody else can work on that if they want. So once you run this Calgary eval, submit all here, and this is just a few of them, but you'd have to do this for every scan in the entire study. It outputs files like these. Let me look at one. So it'll be a file we always try to regurgitate exactly what file names were used. By the way, there's an extra part of the directory here, xt2. That's when we're actually running this. We have even further subdirectories, but I tried to simplify it for this. And this just gives results. Now, if I go down here and I'm gonna just search trabecular thickness. So here's trabecular thickness, I think. If I go up a bit further, it's probably actually not even the trabecular thickness, because IPL sometimes uses the same variables for different outputs. It depends how you're using it. So it makes it very confusing, and you have to be very careful. But somewhere in here, let's find, actually, I know what I'm gonna do. Total BMD. Okay, so I guess I just did, there must be another BMD up here somewhere. Anyways, here I calculate those BMDs. I go in here, it looks like I am calculating the mean unit would be 900, that's probably cortical BMD. And down here somewhere else, there'll be a different result. Actually, this looks another like a cortical BMD, maybe one is with pores and one's without, I can't remember. If you were to try to do this for all 4,000 scans, you of course would have huge errors and mistakes. But as long as you've done the analysis consistently, then all these files are consistent. And so what I've done is I would take all of these log files and I would download them onto my PC. I have to make sure they're in ASCII format. And then I run a Python script. And the Python script has some arguments that I can define. But what it essentially is doing is it's opening up each file in the directory, and it's looking for some key items in it, index measurement, site, and so on. And then it's searching through to look for BMD, cortical BMD, trabecular BMD. It's grabbing all of those things, and it does it for every measurement that we've done in there: moment of inertia, connectivity, even SMI, which I actually don't think we measure very accurately with XT2, but we grab it anyways, just in case somebody might find it useful. And we output that into a file. And for every, I don't have an example of one here, but for every row in that file is the results with columns of total BMD, cortical BMD, etc., that get output. And when you run this Python script on all 4,000 scans, it just takes 60 seconds to grab all of those data. And if it errors out, that means you probably have a log file that has an error in it, and you're going to have to trace it back to figure out what that error is, because something did go wrong in your analysis. So once you get to that point, you finally have some results. This is where I describe how you actually run the Python script with some parameters that you might want to choose. And then the last thing is you might want to capture the overlap. Again, with the overlap, that uses the log files that are in this directory. And it basically does the same thing as the Calgary analysis. When you run this Python here, Python script, it goes through and finds the pertinent data for the volume measurement, because overlap is usually based on a volume of scan. And then once we have all of those scans, overlap measurements, then we can define our overlap. And we always use the denominator is the baseline volume, and then the overlap could be the common volume at any one of those time points. And there actually are slight differences, but as long as you are consistent in how you define that, it should be fine. So, and that's it. You're done. So this is not exactly trivial, but quite feasible to do. I'm going to make all these scripts in this directory available to people, and as well as the parsing scripts, so that they can do it on their own. This file here is a good follow along once you're done with this webinar that you can use to keep track of how you're going. And I wish you the best of luck. So with that, I will finish. Feel free to check bonelab.ucalgary.ca or email me at skboyd@ucalgary.ca, and I can try to help you with your problems, which may be difficult remotely. Come visit us in Calgary. Cheers.